Okay, good morning. Am I audible?
Yes, sir.
Fine. What are the topics that you covered in the last class? What are the topics that you covered in the last class? I want to answer. What?
Binary addition using half adder and full adder method. Binary subtraction using half subtraction and full subtractor method.
Nothing else? What about the utility of execute? Have you studied it in the last class or you have not? Listen, if you do not take a note of my lecture and if you do not follow what we have studied in the classes before coming to the next class, I won't proceed with my lecture. I have given you the notes, the study materials as per the university norms. I have supplied you the study materials, so that is enough. If you feel that is enough, then fine. I won't take any more class. Before coming to my classes, you must make yourself up to date with whatever topics I have taught in the classes. This is the last and final warning to all of you. I'll simply stop taking the classes. I've supplied you the study materials, that's enough. And whatever evaluation process the university suggests, I will go for that one. So to add two opposite numbers, A and B, comparing these two opposite numbers, what can be the result? The width of the result?
Sir, 5-bit.
You should be more precise and you should tell that at most 5 bits. Isn't it? The result will be at most 5 bits. It may be 4-bit or maybe confined within 4-bit also, depending on the values of A and B, isn't it? So after adding these two 4-bit numbers, the result that is sum will be consisting of S0, S1, S2, S3. There may be one S4, which is also called the carry out bit from the sum. C out is nothing but the carry out bit from the sum. This is that S4, the fifth bit. There may be any some carry out, there may not be also in carry out. So there may or may not be the S4 value. Now, to perform this particular A plus B operation, what are the circuit blocks that are necessary?
Half adder and full adder.
Tell me.
Half adder.
You have perfectly answered that half adder and full adder, these two are necessary. Now you have to tell me how many half adders and how many full adders would be required.
4 half adders and
Yeah, very
1
good.
full adder.
Very good. 4 half adders. Anybody else? This is option number 1. Anybody else?
Only 4 for half adders.
Only 4 half adders.
If there is no carry out bit.
No, that you cannot ensure.
Oh,
whenever you are trying to devise a circuit for A plus B operation, you cannot put any limit on the values of A and B.
okay, sir.
So in that case, do you want to modify your answer?
No, sir. No, sir.
Only 4 half adders. Fine.
Sir, 1 half adder and 4 full adders.
Yeah, very good. 1, option number 3. Any other option? Don't be afraid of answering. It may look silly. It may come out to be silly also. Doesn't matter. You come forward with your answer. Don't hesitate. Any other option?
Sir, can't it all be full adder? I mean, I'm just asking.
I couldn't hear you. Please repeat.
Sir, can't it be all the operations full adder? I'm just asking.
How many?
All of them.
All of them means? How many? How many?
Sir, it's 1 half adder and 3 full adders, not 4, I think.
1 half adder plus 3 full adder. Option number 4. Somebody was saying, no, all of them full adders. All of them means what? How many? 20?
4 full adders, sir. 4 full adder.
4 full adders. Okay, let us stop now. Now let us analyze the problem. While trying to go for A plus B operation, we definitely go bit by bit position, 1 bit position at a time, or the 0 bit position. There the input bits are A0 and B0. If you add A0 with B0, the result may be a single bit result or maybe a 2-bit result. Am I clear?
Yes, sir.
If you are trying to add only 2 bits, here it is A0 and B0, the result may be confined within a single bit, or at most it can go for a 2-bit result, isn't it? So the result may be, if it is a 2-bit result, the lower significant bit is taken as S0, and the most significant bit that will become active in the bit position number 1, and that will be taken there as a carry, and that should be termed as the carry which is becoming active in the bit position 1 should be termed as C1. Okay. So from A0 plus B0, I am generating in general, I am generating C1 S0. That S0 will come in the same position, 0th position, but C1 will go to the position number 1, that means the next position. And now, here in position number 1, we have to deal with not only 2 bits, we have to deal with 3 bits. That means C1, A1, and B1. By the way, in the case of the 0th position, as only there are 2 bits to be considered, so there I can I can accommodate this summation scheme using a simple half adder, because in the half adder it can accommodate only 2 bits, is it? So for the 0th position, 1 half adder should be enough. But in case you try to implement the 0th position sum using 1 full adder, what I need to do?
We need a carry.
No. I think it didn't understand the problem. Say I have 1.
We need 3 input.
One. I have 1 FA, I have 1 input. Here the inputs required are AI, BI, and CI. Results are SI and CI plus 1. Here in half adder, the inputs are AI and BI. The results are SI and CI plus 1. When you are in the 0th position, here I can use A0 and B0. Here I can get S0 and C1. But if I decide to use 1 full adder instead of half adder, now this A0, B0 I can accommodate here, because in the case of full adder, it requires 3 input bits, isn't it? In the case of half adder, it requires 2 input bits, and there is no confusion. A0 and B0 will go to AI and BI. But in the case of full adder, it requires 3 input bits, AI, BI, and CI. Now, out of this 3, I have only 2 bits. There is A0 and B0. What about the third bit? What should I do with the third bit?
We can input it 0.
Yeah, that's it. We can simply round it. Just simply round it. That means physically we are connecting the lowest voltage, and as if we are accommodating a 0 there. And here, definitely, in the same manner, the S0 and C1 will be generated. Fine? Is there any confusion in this? So that means for the 0th position, I can realize the required operation using either 1 half adder or a full adder with 1 input bit connected to 0. Clear or still some doubt?
Yes, sir.
Fine. Now come to the position number 1. There definitely I have to accommodate during the summation process 3 input bits, C1, A1, and B1. So definitely you cannot perform this operation using one half adder, you have to go for one full adder, where the three inputs AI, BI, CI will be connected to A1, B1, C1. Clear?
Yes, sir.
Yes, sir.
Fine. Fine. Now, here, after performing the operation of A1, B1 plus C1, A1 plus B1 plus C1 using one full adder, I am generating S1. That is the result will be of 2 bit, at most 2 bit width. The lowest significant bit is termed as the S1, and the most significant bit will go to the next stage as C2. Okay. Now, in the case of addition operation for position number 2, once again I require one full adder. It will generate S2 and one carry may be generated. If it generates, it will come as C3. For position number 3, once again one full adder will be required to accommodate S3, B3, and C3, and the result will be S3, the lowest significant bit, and S4, which is also the C out, that is the carry out generated from this final stage full adder. So I am getting this 5-bit result S4, S3, S2, S1, S0, and this S4 is also called the carry out coming out of the adder circuit. So correct options are either you have to go for one half adder and 3 full adders, or with full adder, 4 full adders, with the least significant bit full adder, 1 bit is connected to ground or 0. Okay, so both these two are correct. Okay, both these are correct. I have implemented this scheme using the full adders only. See, the full adder 0 is the 0th position full adder, where the CI is connected to ground. This is connected to ground. And A0, B0 is connected to A1, B1, AI, BI. SI is generating S0. CI plus 1 is going to the carry input of the next full adder. And A1, B1 are connected to AI, BI. You are getting S1. Now, just observe the circuit diagram or circuit block diagram, and you tell me if there is anything wrong in this circuit.
Sir, in the FA2, the circuit connected to the carry bit is wrong. It should be to CI.
Sorry. Definitely that is wrong. So, anything else? That is, you suggest that it should be like this.
Yes, sir. Yes, sir.
Anything else? Anything else? Any other problem?
So last A3 is connected with BI and B3 is connected with AI.
Oh wow, another mistake. A3 should come here and B3 should go there. Anything else? You get to these other things are correct?
B2 connected with AI.
And A2 connected with CI.
So it should be A2.
Yes.
It should be B2. Now it seems it should be okay, isn't it?
Yes, sir.
Fine. Baba, now tell me one thing. I want to go for 3 plus 5 plus 6. While you perform the addition operation, and you are told that you can add 2 digits at a time. Or rather, no problem. You can add 3 digits. 3, 5, and 6. Will the result be different if I go for 5 plus 3 plus 6, or will it be different if I go for 5 plus 6 plus 3? Will the result be different?
No, sir.
No, sir.
So, in case you add AI with BI, and then with that you add CI, will that be have the different? Will it produce a different value compared to the addition of BI plus CI and then plus AI?
No, sir.
So, in case of, how does it matter whether A1 is going to AI or BI or CI? Ultimately, you are adding this whatever input is in AI, with that you are adding the value of BI, and with that you are adding the value of CI. So whether AC comes in AI or BC comes in AI or C3 comes in AI, does not absolutely matter.
Yes, sir.
So whatever connections were there earlier, all are equally correct. That means in case I connect this CI plus 1 from SA1 to this BI input, but nothing is wrong there. Isn't it? As if I connected B2 to AI, C2 to BI, and A2 to CI. That also performs the same operation of A2 plus B2 plus C2. Because internally it will be performing the operation of AI plus BI plus CI. Are you having any still any confusion?
No, sir.
But for the sake of clarity of the figure, it is always better that I follow the standard connectivity. That means all the A's should go to AIs, all the B's should go to BIs, and all the carries should go to CIs. That looks better for the sake of clarity of the figure. Isn't it? Otherwise, it does not actually matter whether I connect my previous carry output to my A input or B input or C input. It doesn't matter. But definitely, we will try to follow the standard figure. That means the A's will go to AIs, B's will go to BIs, and the carries should go to CIs. Okay, that will simply look better. That's all, nothing else. And here we have mentioned that this 0th stage full adder is equivalent to 1 half adder because the 1 bit, the CI bit has been grounded. Remember, here also I could have grounded this BI and connected B0 to CI input. Are you following it?
Yes, sir.
I could have connected BI or AI to ground and could have used the other two inputs as A0 and B0. Fine. Okay. Then the last class we have seen that for subtraction operation, say I want to perform this your x minus y operation. To perform the subtraction operation, what are the circuit blocks that will be requiring? What are, and then how many of each? First, we answer what are the circuit blocks that will be necessary, and then how many of each. Just like the previous case of addition.
So full substructure and half substructure.
fine. The first part is correctly answered. Full subtractor and half subtractor. Fine. Then the next question is how many of each?
1/2 and 3 full or 4 full.
Yeah, exactly. 1/2 or 3 full or full subtractor or 4 full subtractor. By the way, from the two tables of half subtractor, half adder, full subtractor, and full adder, we have already seen that they are not exactly same. There are differences. So the circuits for half subtractor and half adder and full subtractor and full adder definitely won't be the same, isn't it? The circuit will do what? Whatever truth table is given to the is listed out, it will try to implement that truth table. As the truth tables are different, circuit be the same. The circuit should also be should be different one. So the circuit for half subtractor and half adder, and at the same time the full subtractor and full adder are definitely going to be different. They won't be exactly same. But the problem is, in any large digital system, digital signal processing system, we have to perform a lot of mathematical operations. Now, there are 4 basic mathematical operations: addition, subtraction, then other 2. What are the 4 basic mathematical operations?
Addition, subtraction, multiplication, division.
Multiplication and division. Now, definitely, we know that the multiplication is not a special case of addition. We can go for repeated addition scheme. Or that division that can also be thought about some sort of process of repeated subtraction. So, my basic operations are coming down to only 2: addition and subtraction. So, if my circuit library contains 2 basic types of circuit modules, one for the adder and the other is for the subtractor, I can configure those adder and subtractor modules in such a manner that they can lead to all types of arithmetical operations. Now, here we find that basically in the library I need to have 2 basic circuit modules, one for the adder, the other for the subtractor. But in case I could have, I could have devised one process in which I can perform the subtraction operation using the adder circuit. In that case, for the subtraction operation, also the adder circuit can be utilized. So as a result, only a single circuit module, if that is kept in the circuit in the design library, that can be repeatedly used to realize all sorts of mathematical operations, be it addition, be it subtraction, be it multiplication, be it division. But for that, what I require? I require a process by which I can realize subtraction operation using the addition scheme itself. Is the problem clear?
Yes, sir.
Is the problem clear?
Yes, sir.
I need to perform subtraction operation using addition scheme itself. If that is possible, if that scheme is available, that I can perform subtraction using addition scheme. In that case, basically addition scheme is basically realized using the adder circuit. So only if I have the adder circuit module, that module can be repeatedly used and repeatedly configured as per our requirement to realize subtraction, multiplication, division, all other 3 operations apart from the addition operation. So now my requirement is to realize a scheme or a device scheme where I can perform the subtraction operation using addition scheme. Now this x minus y, okay, I am going for x minus y. This can be realized using class of x, class of minus y. Here, the basic operation I am performing is the addition. But now, what two numbers I am adding? I am adding plus x with minus y. Clear? This x minus y
Yes, sir.
is equivalent to plus of x plus of minus of y. So, to realize this, to arrive at this scheme, what is the basic requirement? The basic requirement is that I need to transit, I need a transition from unsigned numbers to the concept of signed numbers. That is, I need to distinguish between positive number and a negative number. Earlier, so far, we are dealing with only unsigned number. We are not considering the sign at all. We are considering that all are same. There is nothing like positive, nothing like negative. But now, we are requiring a new scheme where I have to provide the concept of positive number as well as negative number. That means I now need one signed number system. I need to arrive at the signed number system concept where I can distinguish between a positive number and a negative number. So number system that is broadly categorized in two domains. One is and the other one is signed number system. So in the case of unsigned number system, all the n bits are utilized for realizing the magnitude of the number. In the case of unsigned number system, all the n bits are utilized to realize the magnitude of the number. So what is the range of numbers that you can realize in unsigned? What is the range of numbers that you can realize in the unsigned number system? 0?
0 to matlab 10 to the power n. 10 to the power n.
10 to the power n. Very good. Welcome that 10 to the power n, isn't it? Anybody else?
So 2 to the power n minus 1.
And lower the bound?
0, 0. 0 to 2 to the power n minus 1.
Minus 1 is here or?
No, sir, there. Former.
Fine. Now we are talking about this. And we are no longer in the decimal domain. We are in the binary domain. So in the case of binary number, n bit will can lead to 2 to the power n number of combinations, and each one of them should represent one decimal number uniquely. So the range should be all 0 to all 1, and all 0 leads to the decimal number 0, and all 1 leads to the decimal number having the value 2 to the power n minus 1. Okay, so that's the. Now, when you go for the signed number system, the concept is a bit different one. Here, one bit needs to be resolved out of the n bits. Out of the n bits, one bit will be set aside a reserve for representing the sign of the number. By the way, how many possible signs are there?
2.
2. So we are lucky. Using a single bit, how many possible combinations you can realize? Using a single bit, how many possible combinations you can realize?
2.
2. So that one bit which I am setting aside for representing a sign is enough. And normal universal standard is 0 is for positive number and 1 is for the negative number. It is a sign bit. So here, this is your S sign bit, and this is the lowest significant n minus 1 bit. Now, in the case of sign number system, there are many categories. Out of it, the simplest one is called the sign magnitude number system. Here, the most significant bit is the sign bit, and lower n minus 1 bit, lower significant n minus 1 bit, they will represent the magnitude directly. The most significant, I repeat, the most significant bit is representing the sign. If that is 0, the number is positive. If that is 1, the number is negative. Or for a negative number, the MSB should be 1. For a positive number, the MSB should be 0. Now, what about the lowest significant n minus 1 bit? The lowest significant n minus 1 bit, they will represent the magnitude directly. There is no transformation, no alteration required. Clear? Should I repeat?
No, sir.
Clear?
Yes.
Or should I?
Yes, sir.
Yes, sir means what? Should I repeat?
No, sir. Clear.
Or is it clear? Fine. So now let us consider one situation where I had a 6-bit sign mag number system. Sign mag means sign magnitude number system. Okay. Using the 6-bit sign magnitude number system, I need to represent class 14. What is the representation? Tell me. Remember, let me do it for you. We are provided with a 6-bit sign magnitude number system. So as it is a 6-bit sign magnitude number system, it will be having 6 total bits, out of which the MSB is a sign bit, and the lowest significant 5 bits they will represent the magnitude directly. Now, what will be the sign bit for this class 14?
0.
Please be louder. 0. Fine. And then I have to represent the magnitude of this class 14, which is 14 itself, using 5-bit combination. So, using 5-bit combination, what is the representation of 14?
0 1 1 0.
Yeah, very good. 0 1 1 1 0.
0.
Okay. So that's the sign mag representation of class 14. Now tell me what will be the minus 20. You do it yourself and tell me the answer.
So in 6-bit form.
1
Yeah, no,
One.
same thing. This is the number system you are provided with.
Sir,
Somebody
it's
said,
1 1
1.
1 0 0 0 1 1 0 0 0.
I don't think so. I think it is minus 24. The big pattern you have given, that is minus 24.
Oh, sorry. 1 0 1
Yeah.
1
Yeah. Yeah.
1 1 0 1 0 0.
1 1
1
0
0
1
1
0.
0 0.
So I'm doing it myself. The sign is negative. So the most significant will be 0 or 1?
1.
1. Now I have to represent the magnitude of minus 20, that is 20 itself, using a 5-bit number system. Using 5-bit, the value of 20 is nothing but 16 plus 4. So this is the sign as representation of minus 20. Correct?
Yes, sir.
Okay, clear? Should I go for any other example?
Clear, sir.
Okay, fine. But actually, why have we gone for the sign and number system at all? What was the driving force for this for going for the sign number system? What is the requirement? Why did you go for that? What was the requirement for going for one signed number system at all? We are quite happy with the unsigned number. Certainly, why are you going for the signed number system?
Sir, they permit us to represent negative numbers.
No, why was that required? Anybody else?
স্যার সাইন নাম্বার সিস্টেম দিয়েই তাহলে স্যার হাফ অ্যাডার আর ফুল অ্যাডার ইউজ করে
Exactly. No. Basically, so we have established the situation that the circuit for half adder and half subtractor, full adder and full subtractor, they are totally different. So I cannot perform the subtraction operation using the addition scheme. But if I want to perform the subtraction operation in the addition scheme, if I could perform the subtraction using the addition scheme, my life would have been much more simpler. My design cost or design library cost will be much smaller. So to achieve that, what we need, that I have to go for this type of operation, x minus y, that should be realized using plus x plus of minus y. So until and unless I can devise certain sign and number concept, I can not perform x minus y using the scheme of plus of x plus of minus y. If I can perform this operation, then only I can think of realizing the subtraction operation using the addition scheme. Now, to achieve that, I need to go for a concept of sign a number. There is a positive x and a negative y. These two I am going to add, which will lead to the result of x minus y. Yes? So what I find is amongst the number system, I have broadly categorized that into two. One is unsigned, the other one is signed. We're going for the signed number system. Why? Because we want to find out one type of representation of numbers which shall allow us to perform the subtraction operation using the adder circuit or using the addition scheme itself. Now let us find out this. We have already devised one type of signed number system representation, that is a signed magnitude representation. Let us find out whether the signed magnitude number system representation is a viable candidate for my requirement. What is my requirement? I need to perform subtraction operation using addition scheme. Let me find out whether the signed magnitude representation of the number is allowing me to perform subtraction operation using addition scheme or not. Let me try to go for the operation of plus 20 minus 14. So that is nothing but okay. And so definitely I have to go for one signed number system, and so far I have gone through only one type of number system, signed number system, that is a signed magnitude number system. So I have to represent this plus 20 and minus 14 using the signed magnitude number system. By the way, here one point you should remember: in case the width of the number system is not specified, I repeat, in case the width of the number system is not specified, only the type of the number system is specified. Here the type of the number system is told to be the signed magnitude number system. I have not mentioned anything about the width. It may be 6 bit, it may be 8 bit, it may be 20 bit, it may be 10 bit. But I have not specifically mentioned anything. Now, in such situations, if it is a signed magnitude or some other type of number system, what we shall do is we will find out what is the maximum number of bits required to represent the number. Here, the magnitude wise, which one is the largest one? Which one is the largest one? 20. Magnitude wise, 20 is the largest one. Now, to represent plus 20, you find out how many minimum bits are required. Use that bit, that number of bits, to be the as if your width of the number system. That is minus 14, minus 10, minus 2, whatever other numbers are there. Everybody should be represented using the number of bits which are required to represent plus 20. Okay. Now to represent plus 20, first of all, it is signed magnitude. So the MSB, the most bit should be 0. And to represent 20, how many bits are required?
5 bits.
5 bits. So, and that should be 1, 0, 1, 0, 0. So, to represent plus 20, I require 6 bits. So, I have to represent minus 14 using 6 bits also. Is the point clear?
Yes, sir.
As if the width of the number system is indirectly provided to you. As if the width of the number system, you are indirectly finding out yourself. Okay. Now, what is minus 14? Tell me.
One zero, 1 1 1 0.
1 0 1 1
1 0.
I think I had written correctly. 1 0 1 1 1 0.
Yes, sir. Yes, sir.
Right. Now I have to perform this addition operation because here I require this. Now what's the result? 0 1 0 with 1 carry, 0 with 1 carry, 0 with 1 carry, 0 with 1 carry. Okay. Remember, the number system, the width of the number system that you are using is 6 bits. Rather, after finding out that to represent plus 20, we are repairing 6 bits. That means as if now you have a 6-bit time mag number system. So now, whatever result you achieve, that should also be represented in 6-bit time memory number system. Whatever result I have achieved is also is representing the result, actual result in time memory, 6-bit time memory number system. Now this comes in the 7th bit position, not in the it is not confined in the 6th bit. So simply that is going out of the number system. Now this is your result. Now this result should also represent, should be representing the actual result in 6-bit time memory system. Now as this bit pattern is representing a number in 6-bit time memory number system, first of all I'll target what is the MSB. What is the MSB? What is the MSB value?
0.
0. So that means the number is, result is
Positive.
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 So the result is positive. Now what about the magnitude of the result?
6.
I didn't get you, Baba. I didn't get you. What will be the magnitude of the result?
So the answer should be 6, but
No,
result is
I'm not bothered about what will be the answer. What I'm bothered is what I'm getting.
The 2.
you are getting 2.
So, though the required answer was plus 6, I am getting plus 2. Let me go for the other thing. Say plus 20 plus 10. I am going for plus 20 plus 10. So I am going for actually 0, 1, 0, 1, 0, 0 and 0, 1, 0, 1, 0. This is the addition operation, isn't it? Okay, let me go for, make it a bit complicated. 20 plus 10, 12. So, okay, this is 20 plus 12. So, remember, I'm actually going for generalized x plus y operation, where both x and y can be positive as well as negative. In case x is positive, y is negative, I am going for x minus y operation. In case x is negative, y is positive, I am going for y minus x operation. In case x is negative, y is also negative, I am actually trying to find out the result of minus of x plus y. And if x and y both are positive, I am actually going to find out the result of plus of x plus y. Clear?
Yes, sir.
Yes or no? In this Bhattacharya, it is the main problem is I cannot understand whether you are getting my point or not. So you have to be please vocal.
Yes, understood.
Fine. So here, as if my x is equal to 20 and y is equal to 12. So I am going for plus 20 plus 12. So what is the result? You tell me. LSB is 0. And 0 plus is 0. 1, 1, 0 with a carry. 0 with a carry. 0 with a carry. So this is my result. 1 and then 5 0. We were using a 6-bit time memory number system. So result should also be in that 6-bit time memory number system. So what will be the result now? what is the interpretation of these 6 bits in terms of the actual result in decimal?
-0.
-0. Okay. So the first of all, the result, though the result should have been my class 32, I am getting a negative result. Here I am getting a positive result. The required was also a positive result, but instead of class 6, I am getting class 2. So definitely, I am not getting my required result using sign magnitude number system. So though that means, what is my inference? My inference is the sign magnitude number system is a valid sign number system representation where I can distinguish between positive numbers with the negative numbers, but it is not that a required number system. By required number, what I mean? By required number system, I mean that it is a particular type of sign number representation scheme where if I use that, I can perform the subtraction operation using the adder circuit, using the adder scheme, addition scheme. But here, using the sign magnitude number system, I cannot perform the subtraction operation using the addition scheme. So it is not that required sign number system representation. But however, it is a valid sign number system representation where I can distinguish between positive number and negative number. Do you get my point? It is a valid sign number system representation where I can distinguish between a positive number and a negative number. But it is not that required sign number system representation which will enable me or you to perform subtraction operation using the addition scheme. I can represent plus 20 using sign magnitude number system. I can represent minus 14 using sign magnitude number system. Both are valid. But if I go for plus 20, plus of minus 14, I cannot pass of result. I cannot get the result of plus 6. I am getting the result of plus 2. So that is not giving me the correct result. Okay. So this sign magnitude number system representation is a valid sign number system representation, but it is not that required sign number system representation which will enable us to perform subtraction operations using addition scheme. So for that, I have to go for some other number system, some other type of sign number system representation. Now there are two other types of sign number representation. One is called R-1's complement, and the other one is called R complement type of number system representation. In the case of R-1's complement number system representation, if where this R is basically the radius of the number system. So for decimal it is 9th complement and 10th complement. For hexadecimal it is 15th complement and 16th complement. For octal it is 7th complement and 8th complement. For binary it is 1st complement and 2th complement. Is it clear to you?
Can you repeat once more?
That the sign magnitude number system representation is not the required number system representation. Is it clear, or should I repeat that one also?
No, so it is clear.
Fine. Now there are to find out one particular sign number system which shall enable us to realize the subtraction operation using the addition scheme. I have to go for some other type of number system, and that number system is R-1's complement number system and R's complement number system, where R is the radius of the particular number system. Now, in the case of binary, the R is 2, so it will become 1's complement and 2's complement. For octal, the value of R is 8, So the 7th R minus 1 is 7. So 7th complement or 8th complement. If it is hexadecimal, it will be your hexadecimal means R is 16. So 15th complement and 16th complement. If it is decimal, R is 10. So it will be 9th complement or 10th complement number system. Now, how to find out the R minus 1 complement of a number? Now, let us first go for the decimal number system. That is R is equal to 10. Okay. Let the given number is x. It's very positive, it's very negative. Now, in case my x is positive, that means x is equal to class of sorry. In case x is a positive number, in that case there is no change in the 9th complement of x. Whatever the representation of x was there earlier, it will be there as it is for the 9th complement. But in case,
Sir, can you repeat, sir?
1 minute. The value of x can be either positive or negative. The value of x can be either positive or negative, isn't it?
Yes, sir.
So let's take one specific example. In that case, it will become clear, easier manner. So let x is equal to 238. Yeah, positive. Okay, so that means I am coming into this category.
Yes, sir.
Fine. In case x is positive, then the R minus, that is plus 238. First I am going for the R minus 1 column, that means the 9th complement representation. Is 238 itself. There is no change. If the number is positive, then the 9th complement or the 10th complement of the positive number is the same number. There is no transformation required. No modification required. Is it clear?
Yes,
If
sir.
the number is positive, then the 9th complement or 10th complement of the actual number remains the same. Of that positive number remains the same. There will be no transformation or no change of the digits required. But if the number is negative, that means in this type of situation, that means x is equal to minus 284. In that case, what it is suggesting is find out the number of digits in the number. How many digits are there in this x?
3.
How many are there in this x? How many digits are there in this decimal number?
3, sir. 3.
3. So simply what we should do is I have to go for r to the power n minus 1 minus the mod. Here r is your 10. N is the number of digits in the actual number. So that is 3. So 10 to the power 3 minus 1 is how much?
999.
999. 999 minus of mod x. Mod x is how much?
284.
284. I have to subtract this from 999. What do you get? 5,
715.
1, 7. So minus 284 9's complement is 715. Is it clear? So in other words, instead of going for the subtraction from R to the power n minus 1, what I am suggesting is simply subtract each digit from 9 and keep the result in that same position itself. That will give you the 9th complement of the that negative number. That will be the mathematical equivalent to as if you are subtracting from R to the power n 10 to the power n minus 1. Isn't it? Clear or not?
Yes, sir.
Yes, sir.
But remember one thing: if the number is positive, absolutely, there is no change or no transformation required. Whatever mod x was there, that will be your 9th complement. That will be your 10th complement. But in case the number is actually negative, I have to go for a transformation. And what is the transformation required? Now I have to subtract each digit from 9. Okay, or as a subtract the magnitude of the number from R to the power n minus 1. Whichever way you want to memorize, you can memorize. But it will be definitely simpler if you consider it that as if each digit you are subtracting from 9. That's it. Fine? Now let me go for the R complement. For R complement, the thing is, once again, for the positive number, there is no change required, no transformation required. Whatever scheme I am telling you, that is relevant only for the negative number. Sometimes I may omit at this point, but you should always remember that if the number is positive, absolutely no transformation will be required in any case. The transformation is required only if the number is negative. And the schemes I am telling you are only for considering the number negative. Okay? So now for the negative number in decimal, what you have to do is you have to subtract from R to the power n. That is as good as in this. Is the left hand side and right hand side the same?
Yes, sir.
So what is this? What is this?
9's complement.
Yeah, R minus 1's complement of minus 1. This is the R minus 1's complement of minus 1. So to find out the R's complement of minus x, I can do what I can do is simply find out the R minus 1's complement of minus x and then add 1 in the least significant position. Yes?
Yes, sir.
First, find out the R minus 1's complement of minus x by subtracting all the digits from 9 or R minus 1 and then add 1 with the least significant position, position of that number. So the so tell me what will be the 10th complement of minus 256. To find out this, what I will do first, I will try to find out the 9th complement of minus 256, and that will be how much? 7, 4, 3. So the
744.
yeah. I won't say it's 744 because it is not in the actual positional number system of the decimal system. It has undergone a certain type of transformation, isn't it? This 743 it is not 743. It is a transformed version of minus 256. Once the certain transformation has taken place, I cannot say that its positional value is 700, its position value is 40, its position value is 3. I cannot say that. So what I should say that 9th complement of minus 256 is 743 and the 10th complement of 256 minus 256 is 744. Clear?
Yes, sir.
Fine. I want to perform this operation using addition scheme. So that means what I need to do is plus 620 plus of minus 168. As the number system we are using is a decimal, either you go for the 9th complement or 10th complement. Let us carry out the scheme using 9th complement scheme. What is the 9th complement plus 622? 620?
Same.
620.
Is 620 or 379?
No change, sir. No change.
No change,
Because
sir.
the
620.
number is positive. Because the number is positive. So what the way I should write is plus 620 minus 168 to be
831.
almost 831,
31.
isn't it?
Yes, sir.
Now you go for 1, 5. Here, basically what you are doing, r to the power n. Okay, by the way, this 620, this is your as if your x, class of x, this is your minus of y. Okay, so what you are basically doing is x plus r to the power this 3 minus 1 minus of y you are doing. Okay, so this is your r to the power 3 or rather here R is nothing but your 10 to the power 3 minus 1 minus of plus of x minus y. Now the value of x, basically this is your mod of x, this is your mod of y. Now the value of mod of x is greater than mod of y, isn't it? Here the value of mod of x is greater, magnitude of x is greater than magnitude of y in this specific case, isn't it?
Yes, sir.
So that means this is greater than equal to 0. In case mod of x is greater than equal to mod of y, this value will be greater than equal to 0. Clear or not?
Yes, sir.
This mod of x minus of mod of y will be greater than equal to 0.
Yes, sir.
So now what I will say is, if I want mod of x minus mod of y from this, I must negate this, I must nullify this, that means I must try to forget about this 10 to the power 3 minus 1. Now, what is 10 to the power 3? What is 10 to the power 3? That is nothing but 1 to 0. Isn't it? The 10 to the power 3 is basically 1000. That means that 1 will come in position number, not in position number 0, nor in position number 1, nor in position number 2, but it will come in the position number 3. That is, if you have a 3-digit number system, this 1 will come in the position number 3. That means it is out of the number system width. Here, one particular 1 will come. This 10 to the power 3. Clear or not?
Yes, sir.
Now, I can do a trick. This 10 to the power 3, if I consider that as if this is a 1 and take it and add it with the least digit position. In that case, the significance of this particular 1 is how much? Is in coming in which position? This is in position number
0.
0. In position number 0, if I have a 1, what will be its positional value?
1.
1 in decimal number system. Isn't it? So if I find that one particular 1 is available here, I shall take it out from that position and take it to the least digit position and add it there itself. If I add it here, so that will cancel out this minus 1. So that 10 to the power 3, so that is leading to 1 in this particular position. So that 1 I am taking from that position and as if I am adding that to the 0th position. So if I take it to the 0th position, that will become 1, magnitude. So that 1, if I add, that will cancel out this minus of 1. So what result you will be getting is x minus of y. So in this R minus 1 complement scheme, to add one positive number with a negative number is, in case after addition, definitely both the operands will be realized in nice complement scheme or R minus 1 complement scheme. I have to add them using normal addition scheme. In case end around carry or one final carry. This one is called the final carry or the end around carry. This end around carry or the final carry, if there is any, I shall take it and add with the least significant position of the result. So I have to add 1 with 451. So the result will become 452. Find out what should be the required result. What is the required result?
So 452.
452. 2. So I am getting the required result. But what you have to do? In case there is any end around carry or a final carry from the summation, I have to add it with the least significant position of the result. Should I take another example? Should I take another example?
Yes, sir.
Say, I want to pass on this. The required result, let me write it down. 141 minus. Okay? That is the required result. I shall try to find out whether I am arriving at this required result or not later. So what is the process? I have to find out, remember where by implementing ninth complement scheme, because R minus 1's complement, here is the ninth complement. You have to find out the ninth complement of both the operands. So what are the two operands here? What are the two operands here? You try to do it along with me, that will help you. You try to realize the sums along with me, that will definitely going to help you. What are the two operands here?
Minus
Minus
264
264 plus 123.
And plus 123. Okay, these are two operands. So you have to find out the ninth complement both the operands. So minus 264 what will be the result of this ninth complement operation?
735.
Tell me, quick.
735.
735.
No, 735. It is not 735. And plus 123. हाँ बताओ ये क्या होगा
123.
123
123.
is it right? Why not 876?
So because it is in positive.
Yeah, the number is originally positive, so absolutely no transformation is required. Whatever negative value was there, that should be your ninth complement. Then what is the next step? I have to add this to ninth complement form. Okay, so 7, 3, 5, 1, 2, 3. This is 8, 5, 8. There is no end around carry or any final carry, isn't it? Is there anything here? No. There is nothing in this question mark position. Clear?
Yes, sir.
Fine. Now, what is the required result?
Minus 141.
Minus 141. Remember, I am performing the addition or subtraction operation using ninth complement system. So after performing this generalized addition, or this is the generalized addition. This plus of x plus of minus y, or this is basically x plus y operation, where in this particular situation x is negative and y is positive. This is basically one generalized x plus y operation, where in this specific case x is negative, it is minus 264, and y is positive, it is plus 123. Isn't it?
Yes, sir.
Yes, sir.
So after performing the operation x plus y operation, where x and y both are represented in ninth complement scheme, the result what you will achieve out of this operation should also be in the same number system. That means after performing the addition operation in ninth complement scheme or ninth complement system, whatever required result is, that should also be available in ninth complement form. What is the ninth complement of minus 141? What is the ninth complement of minus 141?
858.
858.
858.
858.
Sorry, 858.
858.
So after adding this fellow with this, I am getting this, which if I take the reverse transformation will lead to minus 141. That means using ninth complement number system, I can perform subtraction operation or a generalized addition operation where x and y both can be positive, negative, anything using addition scheme. I can perform the subtraction operation using addition scheme using R minus 1 complement representation. Is it clear? Here I have obtained one specific result for a negative result, and in the previous case I have obtained a result for a positive result. Okay, clear or not?
Yes, sir. Clear.
Now let me go for the R complement scheme. I want to perform this. So what is the required result? C. Is it so? I am very weak in mathematics. Please take this and tell me. Is the correct result?
Yes, sir.
Fine. Now I have to perform this operation, that means plus 642 plus of minus 259 using tens complement scheme. So how to, what will be the tens complement of 642?
642.
642.
And minus 259, what will be that? Better I'll do it in two steps. I'll do this in 2 steps. First, find out the 9th complement. That will be your 7, 4, 0.
0.
Then minus 259. Seven, 4, 1. Okay, I am adding 1 with the least significant position. Okay, with this. Now I have to add tell me the result using normal standard decimal addition speed.
1383.
1383. Okay. Now in the R complement, R minus 1 complement scheme, that is 9th complement scheme, in case there was any end around carry or any final carry, we are taking that and adding with the least in disposition of the result. Isn't it? In the R minus 1 complement scheme. Remember?
Yes, sir. Yes, sir.
Now, what I have to do is I have to simply ignore the end around carry or the final carry. That will give me the result. Let me find out the scheme mathematically. This is basically R minus R to the power n minus 1 minus y. That is the R complement of minus of y. This is the R minus 1 complement of minus y. With that, I am adding this 1. So that becomes R complement of minus y. So that is equivalent to, forget about this minus 1 and this plus 1. This is equivalent to R to the power of n minus of mod y. Isn't it?
Yes, sir.
Yes, sir.
Fine. With that, what you are doing, you are adding class of mod x. So mod of x class of R to the power n minus of mod y. That is the thing you are doing by this operation. When you are adding the R complement of mod x, class of mod x, with the R complement of minus of mod y, you are basically performing this operation. Remember, I have considered x to be positive and I have considered y to be negative. That's why I have achieved this. In case my x is also negative, I will get my R to the power n minus of mod x plus of R to the power n minus of mod y. Okay? In case my x and y both are negative, that's a different story. In case you require, I will analyze that. Otherwise, I will simply confine myself to the case where x is positive and y is negative. Okay? So basically, you are having this. Now, this is equivalent to R to the power of n class of this. Now, this R to the power n, this R to the power n is nothing but this carry bit. As explained already earlier in the R minus 1 complement scheme. So, in case my mod of x is greater than equal to mod of y, in that case, definitely there is going to be a valid R to the power n, a non-zero R to the power n. But in case my x is less than y, mod of y, in case my x, mod of magnitude of x is less than magnitude of y, in that case, this value itself will be negative. You can understand this one, this is a very critical point. In case my magnitude of x is less than magnitude of y, this mod of x minus mod of y, that will itself will be negative value.
Yes, sir.
Clear or not?
Yes, sir. Yes.
Yes, sir.
So in case this is negative, this r to the power n plus a negative value will definitely make sure that I won't be getting any carry out. There is sum will be definitely less than r to the power n. In case x minus of mod y itself is a negative value, in that case r to the power n plus that negative value will be definitely less than r to the power n.
Yes, sir.
Yes, sir.
So in case if the thing is less than r to the power n, I cannot get a 1 in the nth position,
Yes, sir.
because in case I get a 1 in the nth position in the sum, that will be basically equivalent to the r to the power n value.
Yes, sir.
Okay, so in case I get a 1 in the nth position of the sum, nth position is basically outside the n digit sum. The MSB of the n digit sum is the basically is the n minus 1th position. If I get some 1 in the nth position, that is for 4 digit case, this is 0, this is 1, this is 2, this is 3, this is a 4 digit case. So if I get a 1 in the fourth digit position, that means somewhere here. If I get something here, some 1 here, that means it is outside the 4 digit width of the number system. So that should be your carry out or the end around carry. So in case you get one end around carry or a carry final carry out, it ensures that the result is positive. And you have to simply ignore this nth position result, because this is already a positive value. So after ignoring this one, whatever value I get, that will be your final result in 383 plus 283. Now let us take for another example where the result should have been negative. One or two examples. So friends, any suggestion? I want to do it. So what should have been the actual result? Minus is it so? I want to perform this using your tensor comparing number system. So what is the process? Plus 2, 4, 3, 8. Is there any end around carry? I do not understand whether you are in the class or you have left.
Please repeat the question.
Is there any end around carry or final carry
No, sir.
from
No,
this sum?
No, sir. No, sir. No, sir.
So there is carry. So that is as if giving you some indication that in case there is a carry generated, the result is positive, and the carry should be ignored, just like the previous situation. In case there was a carry, that is indicating that the result is positive.
excuse me, sir. Sir, your
Sir,
mic
you are
is
not audible, sir.
Sir, your mic is muted.
Can you hear me?
Yes, sir.
Yes, sir.
Because my Bluetooth connection was disconnected. 1 minute. Where I was? Yeah. In case there is an end carry, just like this particular situation where I tried to add class of 642 with minus of 59, there I generated one. I found that one end carry or a carry, final carry was generated, and I have to simply ignore that final carry, and the result is a positive value, and there is plus 383. So the indication that end around carry or the final carry is giving me is that the operand, the result is positive, and the result can be directly obtained. But in case there is no end around carry, here you find that there is no end around carry. There is nothing. There is no end around carry. So no end around, this is called end around carry. Or which is also called the final carry. So in absence of end around, any end around carry or the final carry, I can infer that the result is negative. And in case the result is negative, I cannot find out the magnitude directly. To find out the magnitude, what you need to do? You take its R complement again. What is its R complement?
3842.
3
Minus 3842.
1 plus 1.
Yes, sir.
So 2, 4, 8, 3 with a negative sign. So the result is this. To find out the actual result, I have to take its 10th complement again. That is first 9th complement and then add 1 to find out the result is minus 3, 8, 4. So that is the. Okay?
Yes.
Yes, sir.
Somebody is raising any issue, I think. Very simple voice. Anybody? Anybody is having any problem? Please be vocal. I become angry only when you do not raise your voice. I never become angry if you raise any silly question also. So please do not hesitate. If you have any problem at any point of time, please raise your voice. In the class, I asked you to raise your hand, but here I cannot see you. So please raise your voice. Anyway, one thing is sure that using both the 9's complement, that R minus 1's complement or R's complement scheme, I can perform the subtraction operation using the addition scheme. Now, our main intention is to deal with the binary system. So we have to go back to the binary number system, and there the R minus 1's complement scheme should be termed as
1's complement. R minus
1's,
1.
and the R's complement scheme should be termed as the 2's complement scheme. Okay, so now we have to go for the one's complement and two's complement scheme. Now in the one's complement scheme, once again I have to subtract from 2 to the power n minus 1. Definitely, I repeat once again, absolutely there will be no transformation required. The transformation will be required, that means 2 to the power n minus 1 minus the magnitude thing I will be doing only if the number is negative. In case the number is positive, once again, whether it is 1's complement, whether it is 2's complement, absolutely no transformation will be required. Transformation will be required only when the number is negative. So whatever I am saying or I will go to say is meant for only the negative number. So here I have to subtract things from 2 to the power n minus 1. Now the 2 to the power n minus 1 is how much? Now all n bits should be 1. If I am dealing with 6-bit number system, n is 6. So 2 to the power 6, that is 1, then 5 zeros. That minus 1 is nothing but 5 1. So I have to subtract x, mod of magnitude of x from 2 to the power n minus 1. That means I have to subtract all 1. Now the constituent bits of x are either 0 or 1. Isn't it? Constituent bits of x can be either 0 or 1 because it's a binary system, so x constituent bits will be either 0 or 1. So I'll be subtracting either 0 from 1 or 1 from 1. If I subtract 0 from 1,
1.
1. If I subtract 1 from 1, what will be the result? 0.
0.
So now basically I don't have to go for the actual subtraction operation at all. What I have to do is I just simply go for the bit-wise complementation. If it is 0, I have to go for 1. If to 1, I have to replace it by a 0. So I have to simply go for bit-by-bit complementation. That means absolutely no arithmetic operation I will be taking for finding out the transformation. Simply bit-by-bit complementation I will be doing. No subtraction operation will be required here while generating this to the power n minus 1 minus of mod. Simply I have to replace each bit of minus of mod x by its complement bit. So for example, if I have a minus 24 in in 6-bit 1's complement system, what is the representation of minus 24? In 6-bit 1's complement number system, what will be the representation of minus 24?
1 1 1 0 0 0.
The answer is 1 1 1. Let me do it myself.
This is the minus 24 6 bit.
I don't think so. What I have to do is to find out the ones complementary number system. My starting point should be the number considering it to be positive. I repeat. While finding out the ones complement of any number, be it positive, be it negative, be it positive, be it negative, any number. My starting point would be the sign magnitude representation of the number considering it to be positive. I repeat, to find out the ones complement of any number, my starting point will be the sign magnitude representation of the number considering it to be positive. That means the first step is find out the sign mag representation of the number considering it to be positive. I emphasize on the term considering it to be positive. I am not bothered about what is the actual sign of the number. I will consider the number to be positive. Let the original number be positive, let the original number be negative. I don't bother. Always we should think positive. So take the number to be positive also. So assume the number is positive and find out its ones is sign magnitude representation. So here in 6-bit ones complement scheme, that means the width of the number string is 6-bit. So first assume that the given number is positive. That means you are not given minus 24, you are given supplied is plus 24. Find out the sign mag representation of plus 24 in 6-bit scheme. What will be that? Sign magnitude
0
of
1 1
0
0 0
1 1
1 1 0 0 0.
Okay, so this is that is okay. That I should where I should write. Okay, okay. So plus 24 sign mag 0 1 1 0 0 0. Fine. So I have assumed the given number is positive because I am always a positive thinking fellow, but not for the COVID situation. There, everything should, all of you should be negative. So here I am assuming the number to be positive. So for plus 24, the sign and representation is given by 0 1 1 0 0. Now find out the actual sign of the number. What is the actual sign of the number? Positive or negative?
Negative.
Negative. Now here I am having a certain if-then type of if-then else type of clause. If the number is originally positive, this is the ones complement representation. Now that sign as representation. If the number is originally positive, this is the sign. This is the ones complement representation of the number. However, if the number is take bit by bit complementation of the sign mag representation to arrive at the ones complement of the number. Should I repeat?
Yes, sir.
If the number is positive, this is the ones complement representation. That means this is the ones complement representation if the number is originally positive. Okay. And if you are asked to find out the 6-bit ones complement representation of plus 24, this is that. Because I have already told you, so for R complement, R minus 1 complement number, if the number is originally positive, actually no transformation will be required. So I am not going for any transformation, and this is the one complement representation. In fact, this will be the two complement representation also later on I'll find. But if the number is originally negative, the case is bit different. Now, to find out the ones complement of the number, I have to take bit by bit complementation of the sign match representation. Sign match representation of the number considering that to be positive. My starting point was assume the number is positive. I am not bothered about whether the number is positive or negative. I am assuming that the number is positive. I am finding out the sign match representation. This is the first step. After that, obtain the sign match representation of the number considering that to be positive, I have to actually go for taking the actual sign of the given number. If the given number is actually positive, the task is very cut short. This is that one complement representation. This is the two complement representation. This is the one sign. So sign representation, one representation, and to all three will be absolutely identical if the number is positive. If the number is negative, will be once again the number considering it to be positive, and I have to find out the sign match representation of this is the starting point. Now, as the number is originally negative, I have to take it bit by bit complementation because I have to subtract mod x. This is your mod x from 2 to the power n minus 1. That means I have to subtract every bit of x from 1. Now, subtracting a bit from 1 is equivalent to complementing the bit itself. So, minus 24 once complement is the bit by bit complementation of this fellow. It is 1 0 0 1 1 1. Is it clear?
Yes, sir.
Yes, sir.
You do one example. Find out, you assume that the number system is 6 bits once complement. Find out the ones complement of minus 17 and plus 12. You try to do it yourself.
Sir, the first one is 101110.
The first step is to go for you told it correctly. What about plus 10? Once again,
0 0 1 0 0.
0 0 1 1 0 0.
001100.
0 0.
but once again, I have to follow the same process. Sign lag of plus 12 in 6-bit system.
1100. Yes.
Then plus 12. Okay. This way you should write. Starting point is the number considering that to be positive. Find out the sign match representation. Then you have to take for whether the number is originally positive or negative. As the number is originally negative, I have to take bit by bit complementation of this to arrive at this. As the number is originally positive, so this is the once complement is completed. No bitwise completion is required. Okay.
Yes, sir.
Is it still clear about how to generate the once complement of a number, whether it is positive or negative?
Yes, sir.
Yes, sir. Clear.
So please, before coming for the Friday class, you please go through the schemes for R-, so once complement addition, generalized addition, and R complement generalized addition, and how to arrive at this once complement representation of any number. I will continue from this point. If I have to start from 0 again, then I will really face a problem. Please help me. Okay, so I'll call it there now. By the way, in the next class also, I'll follow the same knit link. I don't think I need to generate knit link every day. Can I not use the same? I'm asking for a suggestion because you are more conversant with the technology than us. The same knit link in the next class also, or
So same link.
in all the classes?
Same
Same link.
Same link is better.
Okay, that means whatever link today I am using, I'll follow that one.
Okay, sir.
Okay, I won't send you any further link.
Okay, sir. Okay, sir.
Okay, please convey it to your friend.
Yes, sir. I will tell the CR.
Okay, fine. Fine. And in the Friday's class, as after my class, there is admin class. So I have to stick leave by 5 minutes plus 2:12. So please try to join the class by 5 minutes plus 10, not later than that. Okay.
Okay, sir. Okay, sir.
Bye. Thank you.
Thank you, sir.
Welcome.